Hello, students. Welcome to today's session. In today's session, we would be starting a new chapter that is kinematics. In our previous class, that is on the online Google Meet, we have already completed, dimensions and scalar vector, and we have also seen the basic derivatives and integration formulae which we would be using in physics, right? So we are all set to start with kinematics. So let's get going. Okay. So the flow of topics that we would be covering today would be we would be starting this new chapter kinematics. Okay. And in in our today's discussion, we would restrict our discussions to kinematics or rest and motion in one dimension only. We would be covering the two dimensions and three dimensions later. Okay, but today's intent is we would be covering our discussions around one dimension. Okay, so we will start with understanding what is rest versus motion. Okay, so when we say something is at rest and motion, few more concepts related to that we would try to understand. We will go over to define something called as frame of reference. Okay, and students, this is a very interesting and important part, so please, I would encourage you to be very attentive to this one, because if you pay right attention to this, you need not mug up a lot of formulae which people tend to mug up. Okay, so this would help a lot. Okay, and then we would go ahead to define some of the important physical quantities which we would use throughout our study of kinematics. So some defining physical quantities like your position, your displacement, distance and displacement. We would study your average and instantaneous velocity, acceleration, time taken. Okay, so we would go through those things. Okay, next we would go over and we would walk through the regular, derivations or regular deductions of kinematics, which you would have also studied in your high school level. The formula is like, S equal to UT plus half AT squared and couple of more, right? So we would be doing that. And then we would be moving over to some practice problems, okay? So this is what we are trying and aiming to complete in today's video. So let's get started. So coming to rest and motion, right? So we may think for a moment that, hey, we have been, talking about things that are at rest or things that are in motion right from our childhood. So obviously you might be thinking that you are the very room from where you are watching this video, you are sitting, and maybe you are sitting in front of a camera or a phone or a laptop. So that is at rest that is at rest, right? The room where you are sitting, the walls of that room, they are at rest. But a vehicle which is moving outside your home, that is in motion. A rocket that might be flying in air or a bird that is flying, that bird is in motion. So what is so important that we are trying to discuss and understand that as a subject matter in physics. So let's try to demystify that and understand what are some of the key things in that, right? So now let's just take our debate to next level, right? So and let us just define with one of the examples of the things which I said. Okay, so say I have a student, or I have a student, Ram. Okay, he is sitting in a room. Okay, and he is watching my video live using his laptop. Okay, so this is a table, there's a laptop here, and obviously he is watching my session live on this you know sitting in a room. Okay, so now Ram says that this laptop is at rest, correct? Similarly, so let's take just this example. And why does he say that it's at rest? Okay, so say at 7:00 p.m. India Standard Time, okay, he found that the distance between him and this laptop was suppose you know it could be probably 30 centimeter. Okay, so or maybe yeah, 30 centimeters sounds logical, so it's just a hand apart from him, 30 centimeter. At 7:01 p.m., after 1 minute, the distance would continue to be 30 centimeter. At 7:05, and I'm assuming that he has not gone for a loo break or anything else, right? And the laptop is also not moved, right? So as long as that continues, the distance does not change. So here we go into one level deeper, that when position does not change while, or with the flow of time, then we say something is at rest, right? So that is why Ram will say that his laptop is at rest. Okay. Similarly, if Ram were to talk about this table, or he would say that yeah, this table is probably 20 centimeters from him. And again, along with passing time, the position of this table from him is not changing. So that's why Ram feels that this table is at rest. Similarly, any wall of this room or the roof, the position is not changing. So the key is, we have written here, when position does not change with the flow of time, then we say that something is at rest. Now, one very important and key thing which is missing in this entire statement, let us try to understand that with an example. Okay, so say, okay, so he feels that Ram himself is at rest, right, in this entire example, because all of us feel we are sitting in a particular place, we are at rest. But do we not know that Earth revolves around its own axis, so that it completes one revolution in 24 hours? So, which means you, me, and everyone who is sitting at a particular place and feeling that he or she is at rest, ideally, he or she himself is not at rest, right? Similarly, similarly, we know that we move, or Earth moves around the sun. So all of us are moving around the sun, right? So which means the table or the laptop which appeared to be at rest to Ram in this example, right? So this laptop appeared to be at rest to Ram, right? But if suppose somebody observes it, being say sitting in moon, he or she will feel that, oh, you know what, Ram and the entire room and this table and this laptop is moving at a high speed along with Earth, so it is not at rest. Okay, so that's why, remember students, one very important thing that is missing in this statement is this word. Okay, that is somehow this pen is not working. Give me a moment. So a very important word is with respect to. Okay, with respect to. So remember, this is the very reason why we say this laptop is at rest with respect to RAM. This table is at respect with respect to RAM. Similarly, if there is some way to observe RAM from this table and laptop, RAM is at rest with respect to the laptop. RAM is at rest with respect to this table. But all these things are in motion with respect to someone sitting in moon, right? Or with respect to someone going in a spaceship. Okay. Or similarly, if let us take one more example. Okay. So say I'm traveling in a train. Okay. And while traveling in train, let me rather take the example of a flight, right? So say I'm traveling in a flight. I ordered a meal, okay, and the air hostess comes and delivers it. Now I opened up my meal and I wanted to eat my sandwich, right? So the moment I opened the sandwich and I start eating it, I open the tray in front of me, place it there, and start eating. Right. So obviously, when I am flying in an airplane, right? So obviously, I am moving at a high speed. The tray in front of me is moving at a high speed. The food that I have kept there and started eating, even that is moving at a high speed. But I feel as if that table is stable. I have or the tray was stable. I kept my food. I felt as if it is at rest, and I started eating it, right? Or else, if somebody sees it outside the plane, he or she would feel that, or find that I'm moving at a very high speed. The tray and the food is also moving at probably at the same speed in the same direction, and that is why I feel those things are at rest, and somebody else feels that I'm in motion. So this is a very important word again here, feels, right? So we feel something only when it is with respect to something, right? So for example, if somebody is a millionaire, probably you and I will say them, he's a rich guy, right? But probably if you go and ask Bill Gates or or an Anil Ambani, they would say, yeah, he's just an average guy who earns pretty less than me. So he could be just a normal guy or a very poor guy, right? So remember, students, in our normal life or in physics, almost everything that we define is relative by nature. So whenever we talk about rest and motion, we would always talk with respect to something. Okay. And what is that something? The answer is with reference to some frame of reference. Okay. And I have introduced this word now, frame of reference. Okay. Frame of reference. We will look into it a little details in few minutes. Okay. So in this situation, Ram himself is the frame of reference, right? Because Ram is the speaker, he is speaking. So whenever we speak with respect to ourselves, right? So if you want to understand this analogy, just go by that calling out a person rich or poor, right? So I will say that somebody who is a millionaire is very rich, but Dhirubhai Ambani, with respect to himself, or Anil Ambani or Bill Gates will say he's a poor guy, right? So similarly, somebody with a 5'6" height, I'll say he is tall, but a Russian guy probably would say he's a very short guy, right? So that is why the default frame of reference many times is the speaker himself. So here, Ram was the frame of reference, and in this frame of reference, when he found that when position of something does not change with the passage of time, with respect to himself or herself or the frame of reference, then we say something is at rest. And when the position is changing, we say that that body is in motion. Okay, so let us try to depict it in a graph. So let us try to understand this a little better. So if I were to draw a graph to indicate this is how it would look like, right? That say I represent time, which is the independent variable along the x-axis, and I represent position, which is the dependent variable along the y-axis. Okay, if I represent it like this, right? So at 7 p.m. the distance was suppose 30 centimeter. So which means this is nothing but 30 centimeter in this graph. Okay. Then at 7:05 distance was again same. At 7:10 distance was again same. So at 7:15 it would again be same. So if you see, if we join all these lines, we would end up getting a straight line, right? So if position or position vector is along this direction and time is along this direction, then this would be the graphical representation of something that is at rest with reference to the frame. Okay, so this is, and these graphical representations would come handy in some of the practice problems that we would see. Okay, now let us obviously go and understand what would be the motion. Okay, so if 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 something is in motion, so at 7 p.m., so 7:00 p.m., probably the distance was 30 meter. But so assume that one bird was sitting on round table, and then it started off and it flew away, right? So if it flew away, then at 7:05, probably if it has traveled slightly, so probably the bird could be at 100 centimeter distance or maybe 100-meter distance at that time. Okay, so something again at different time, the position would be different. Okay, so which means that would be kind of a graph here, right? So which, when position changes with reference to time, then we say that a particular thing is in motion with reference to the frame of reference. Okay, so any question on this one, guys? If you have, you may type down in the chat box. I give you few moments and then we will move on to the next question. Good. So I didn't see any question. So let's keep moving. Okay. Now, now let us move a little bit. So one more interesting thing, if you see here, okay, that so we have introduced something called position, right? And in vectors, we had read position vector. Okay, so we would use this concept now in kinematics. Let's see how we would use it. Okay, so say let us go to the same example. Okay, so time, and say this is your position. Okay, now this is the origin O. Okay, so initially the bird was here, then it flew like this, like this, like this, like this, and it came back and it probably said at a different point. It started from A and it set at B. Okay, so students, this entire length that this bird has covered in this entire journey, that in physics is called distance. Okay, so distance is nothing but the length of the entire journey while while the object was in motion. So this one we would say that this is the distance, but there is one more term which we would introduce called displacement. Displacement. And obviously, if you go to the lexical definition, we'll get it. How much it has got displaced. It started from A, moved in this path like this, like this, like this, like this, and finally came to B. So in that scenario, obviously, the displacement would be join the starting point and the end point and draw a arrow from starting to end. This we will say as displacement vector S. So most of the times we represent the displacement vector with the letter S. Okay. So now distance and displacement. So we have already introduced two terms, distance and displacement. Okay. Now let us try to understand a new sorry a next set of couple of physical quantities with this. Okay, and before that, let us stop for a moment and let us understand one more a couple of other things, right? So and because in the chapter unit dimension, I have said you that as and when I introduce any new physical quantity, I would be talking to you about its units, its dimensions, so that things become more and more clear to you. So distance. So distance is nothing but this is a length only, right? So obviously its dimension would be mass 0, length 1 times 0, right? And units, very simple. The SI unit is nothing but your meter, okay? And your CGS unit is centimeter, okay? I'm just giving two examples, and then obviously there are many units of length or distance, so that you can keep reading from different places, right? So throughout the course of physics, okay. Now similarly, if we say displacement, okay, if we say displacement, this is also a length. So obviously dimensions will be same, units will be same, right? So I have something called distance, okay, and I have something called displacement, okay. So can I say, and I found that their dimensions are same, okay, their units are also same. Okay. So if the dimensions are same and the units are also same, can I say that distance equals to displacement? Okay. And the answer is not necessarily, and most of the times no. Mostly no. Because first difference, this is a scalar quantity, this is a vector quantity. Okay. So this has got no direction and this has got a direction. Okay, this this. So if I say 2 meter plus 3 meter, it is always 5 meter. So it gets added as per your algebraic addition, and vector gets added as per vector law of addition. Vector law of addition, which means if 2 meter is along this direction, 3 meter is also along this direction, then I can say the addition of both of these will be 5 meter along the same direction. If 2 meter along this direction, 3 meter along this direction, then I would say the net displacement is only 1 meter along this direction. And if there is a separate angle, then we need to find out what would be the net displacement. So I need to complete the parallelogram law. So this would be the resultant. Okay. So that's why displacements are added as per your vector law of addition, but distance we can add as per your algebraic addition. So there are many differences. Okay. And one more interesting thing is, if you see, most of the times, most of the times, distance is distance is greater than or equal to the magnitude of displacement. Okay, most of the times distance is greater than or equal to the magnitude of displacement. And this is, you can understand it very easily, right? So suppose this was the loop, right? So distance would have been probably something like your 300-meter, but displacement would have been just this much. Okay, so it's very easy that in this case, the distance is this entire length and displacement is just this much, the magnitude of displacement. So this is more. Sometimes, if the bird would have come back and sat at the same place, so displacement would have been zero. Displacement would have been zero, but distance will be the entire loop, right? Sometimes, when a body is moving in a straight line, at that time, the magnitude of distance, sorry, the distance and magnitude of displacement, they may be same, but most of the times they are not. Okay, now with these examples, right, so let us try to solve. Okay, so let us go to the next set of definitions and understand a couple of more things. Okay, so now let us move on and understand a little bit about frame of reference. Okay, and students, frame of reference, I would teach you around 4 times in my entire physics course. So first time we would study here, second time towards the end of kinematics, when we would study the relative velocity. At that time I would add some more concepts. Similarly, when we go to Newton's laws of motion, and obviously we would add something else called inertial frame of reference and non-inertial frame of reference. And again, at the end, when we'll go to the theory of relativity, I would add again something more to frame of reference. So frame of reference concept could be a little complicated if I give everything in one shot. So I would slot it in this gradual progression. Okay, so let us understand about frame of reference, what we need to know right now. Okay, so normally in physics, we use a three-dimensional Cartesian coordinate system. Okay, we normally use, and I'm again saying we normally use, or most times we use. But again, if you want to take something else as a frame of reference, you can always do that. No one stops you. Okay, we use the three-dimensional Cartesian coordinate system as the most conventional frame of reference. So you will have three axes, right? So obviously, if this is your x-axis, if this is your x-axis, this is your y-axis, then this would be your z-axis, right? So we would, and we have studied in vectors that unit vector along x-axis we call I cap, unit vector along y-axis we'll say j cap, and unit vector along z-axis we call k cap, right? And they meet at a point origin, that is O, and we know that each of these axes are at 90 degree to each other. So and we have also seen in vector chapters that to visualize how your Cartesian coordinate system looks, look at any corner of your room, right? So any corner of your room, you would see there are three directions meeting at the same point. So you can name two of them as x and y, and then the third perpendicular one would be z. And see students, with these three coordinate systems x, y, and z meeting at an origin O, we can define the position of anything in any of these three dimensions. Okay, and couple of key points that we need to notice, right? And we have defined this is positive x. If this is positive x direction, this will be negative x. If this is positive y, this would be your negative y. If this is positive z, something like this would be your negative z direction. Okay, so as it would look complicated, I'm just removing it the negative axis as of now. Okay, but obviously in the opposite direction things will be negative. So first point, right, in the card, so first point, normally we use the three-dimensional Cartesian coordinate system as our most conventional frame of reference. Second point, all the three axes are perpendicular to each other and they meet at the origin O, right? Third thing is very, very important. We have defined I cap, J cap, and K cap as positive as unit vectors along positive x-axis, positive y-axis, and positive z-axis, which means I will say 3.1 and 3.2. 3.2 would be anything in the opposite direction. Okay, opposite direction, we would go with the negative sign. Okay, remember, if you understand point number 3.1 and 3.2, you need not mug up a lot, at least few of the formulae which people mug up. Okay, and I can bet you mostly in your high school also you would have mug up. Okay, we'll get to that in few minutes. Okay, now along with that, let us go to point number 4. Point number 4 is the fourth dimension that we use is time. Okay, so that's why any point P in this Cartesian coordinate system can be defined by its x, y, and z coordinate. So with x, y, and z coordinates, we are defining the position of something. Okay, and fourth coordinate we say is time. So when position and time is defined, you remember students, everything related to that body is defined in kinematics. So maybe in some of the fancy examples you would have heard about 4D printing, or 4D, 5D, or probably movie in 4D, movie in n dimensions. Remember, as per your classical physics, anything and everything, its position and time could be defined just with the four dimension position with x, y, and z, three dimensions which are in accordance with your Cartesian coordinate system. And fourth one is the time dimension. Position and time are defined, it's done. Anything and everything else that you see in the fancy world, they are more to I mean, it could probably be correct as per their domain, but not in physics. In physics we have these four dimensions, and even in relativity also most of the things can be defined just with these four dimensions. So I don't think we would be adding anything fifth dimension or sixth dimension, at least in the curriculum of plus two physics, in the entire course. Okay, now this is about frame of reference. Now I would again pause just for a moment. If there is any question you want me to repeat or highlight, or you could not understand, type down in the chat box, and then I would move into the next set of definitions. I would pause for a few moments, and I would use that time to erase the whiteboard. Okay, let's see if there is any question pasted in the chat box. Okay, no question. Good. Let's get going. Okay, so now let us define something called as speed. Okay, we'll start with speed, and then we will go to something called as velocity. Okay, so we would start speed like this, right? That, and I would start it with a term called average speed. Okay, So say when position of something changes with time. So this is a graph, right? When position of something changes with time. So from a time interval, suppose your t equals to your t1 to t equals to your t2. In this interval, whatever the distance this guy has covered, right? So if I do the distance, your change in distance by change in time, this is called nothing but your average speed. So average speed is nothing but your delta in the distance. So what is the change in the distance, or how much distance the body has covered versus how much time it elapsed, right? So when we say he is moving at 30 kilometer per hour or 100 kilometer per hour, what are we saying? Kilometer per hour. So in a span of 1 hour, the average speed of this train is probably suppose 100 kilometer per hour. So if this train runs for 1 hour continuously without changing anything, so it would cover a distance of 100 meter. Okay, so maybe we'll just see that as a very small practice problem, right? So suppose, so we can quickly see this practice problem that a motorist a motorist covers a distance of say your 72 kilometer 72 kilometer in in 2 hours. Okay, then find out his average speed. Okay, so very simple. Average speed, we know, change in distance by change in time. So this guy covered how much of distance? 72 kilometer. 72 kilometer in how much time? 2 hours. So 72 by 2, that is nothing but 36 kilometer per hour. Okay, okay. Or if you want to convert it into your meter per second, then you can do 36 into 1 kilometer is 1000 meter by 1 hour is 3600 second, right? So these two zeros and these two zeros cancel out. 36 cancels out. So he is also traveling at 10 meter per second. Okay, so you can either express in this unit or any other unit. If you want to go by centimeter per second, your call. So it depends on how it is expressed in the problem, and you can just use the same one, right? So the basic thing that we have seen, the average speed is distance covered divided by the time elapsed. Okay, so now if you got that, let us go back to our original method. Now we have introduced one more physical quantity called average speed. Okay, so what would be the dimensions and unit of it, right? So dimension would be nothing but dimension of dimension of distance by time, right? So we know distance is nothing but a length. So I can say this is nothing but m0 l1 t0 by time is t1. So this is nothing but m0 l1 t minus 1, or people say the dimensions are 0 1 minus 1 in terms of mlt. Okay, or you can simply say it's lt minus 1, whichever way you want to express. Okay, so these will be dimensions. Units, very simple. Distance is measured in meter by time in second. So your SI unit would be meter per second. What would be the CGS unit? CGS unit would be distance is measured in, okay, let's draw a line here. Okay, so CGS unit would be distance is measured in centimeter, time in second. So you can say centimeter per second, meter per second in SI, and centimeter per second in your CGS system. Okay, interesting, right? So now let us see one one. Let us now see the graphical representation of this and understand that graphical representation part. Okay, so let us go to the graphical representation. So okay, or let's do one thing. We'll first cover one more thing called instantaneous speed, and then we'll see the graphical representation. Okay, so this is about your average speed. Okay, now let us go into something called as your instantaneous instantaneous speed. Okay, instantaneous speed. Instantaneous speed would be nothing but, so say I said the position of this was changing like this, right? So, and we have defined that your average speed average speed was delta distance by delta time. So at any given moment, right, at any given moment, the small distance it will have covered, right? So in that moment, the distance it will have covered by the time, that would be your instantaneous speed. So if you see, the the riddle gets resolved if you follow the nomenclature. It's instantaneous at a given instant. What is the speed? At that point of time, delta s by delta t. But if your delta t is absolutely zero, then you cannot find out the difference between delta s to by delta t, right? So we would use the limit concept here. So if your limit delta t tends to delta t tends to 0, delta s by delta t. If you do this, then what we get, that is called as your, so I can say it is d by dt of s. We have already seen this derivative concept in our previous class. Okay, or if you want, you can also say ds by dt. Okay, so this instantaneous speed, v instantaneous, is nothing but your ds by dt. And as we said, as we discussed in derivatives, don't say that dd cancels out, so it is s by t. No, it is not d into s and d into t. It is actually d by dt, which is a derivative function of speed, or your position. Okay, so yeah. Now, if we have understood this instantaneous speed, and students, in today's class, we would also see a couple of small problems on average speed and instantaneous speed. Okay, so we will look into that in a few minutes. Okay, now let us let us introduce one more physical quantity called called velocity called velocity. Okay, so we will start with a similar thing, average velocity. Okay, so average velocity is defined as, average velocity is defined as the change in displacement. Okay, change in displacement over change in time, or we can say average velocity VAV equals to change in displacement by change in time. But one interesting thing, if you see, displacement is a vector quantity, and we have studied in your vectors chapter any vector A if it is multiplied by any non-scalar constant. So when I'm saying divided by, that is nothing but 1 by any scalar. So vector into 1 by any scalar will also be a vector only, correct? So that also proves that your velocity, as the definition says, is a vector quantity, as it is displacement vector divided by time scalar. Vector divided by a scalar, the resultant will always be a vector. Okay, so that is why average velocity is a vector quantity. And if you see also in the first example that I told you, that Ram is sitting, bird goes and comes back, right? So we have seen this was suppose your distance, right? Then this would be your displacement vector. So I will say that average velocity is nothing but the displacement vector. I can directly say, okay, displacement vector by your change in time, right? Or if I want to say the magnitude of change of displacement, no, here I put a vector sign, so I can continue the vector sign. So it's nothing but the displacement by the time elapsed. Okay, so again we can understand this thing very quickly, that what would be the dimension of velocity. While finding out the dimension, I can remove the vector sign. It's not needed because I just need displacement by time, which will again be same, no difference. So this is nothing but a length by time. So I can say mass 0, length 1, time 1, MLT minus 2. So again, if you see the analogy between your distance and displacement, if you replace distance and displacement, if there's an analogy, then the corresponding thing would be your speed and velocity. So this will say speed, and this is your velocity. Okay. So obviously, what would be the unit? The unit would be unit in SI would be meter per second. In CGS, it would be centimeter per second, right? So quite simple. Okay, no rocket science really in that. Okay, so good. So these would be average speed and velocity. Okay, now let us solve a quick practice problem. Okay, so and after that we'll see a couple of things on graph. Okay, one more. Okay, wait. I think let us cover one more thing related to your instantaneous velocity, like we studied for instantaneous speed, and then we'll go to practice problems. Okay, so let us now introduce your instantaneous velocity. Again, it will be similar, that when your limit, your delta t tends to 0, which means at any given instant, whatever was the velocity, your delta s by delta t, which is nothing but your ds by dt, that is called as your instantaneous velocity. Okay, so yeah, so in a scalar form, you can say instantaneous velocities magnitude would be your ds by dt, or in other words, d by dt of s. Okay, or if you want to put it here, d by dt of s. Okay, now let us go back and do one or two practice problems related to average speed. Okay, other things are pretty straightforward. Instantaneous, it would be a little easier. So let us start with average speed, and we would see the tweak and trick in that. Okay, so the practice problem says a motorist a motorist travels at a speed of at a speed of, say, your 36 kilometer per hour for first 30 minutes, and then 72 kilometer per hour for next 30 minutes. Okay, then find out find out his average speed. Okay, find out his average speed. Okay, first thing, find out the average speed, and then a second part of this is find out the distance covered by him in first 30 minutes, second 30 minutes, and in entire 1 hour. Okay, so this is the practice problem. I will give you few minutes to solve. Okay, and then we would go ahead and solve it on the board. So I would go mute for a moment, or for some time. I'll allow you some time to try to solve it, and then we would see how we'll solve it on the board. Okay, so I think let us solve it on the board in the interest of time, right? So yeah, and then you can probably, yeah, or practice a lot of problems like this at home later. Okay, so I would just not rub the figures so that I don't forget them. Okay, because I have just coined it out on the fly. Okay, and we need to find out few things here. Okay, now, so the problem says first 30 minutes at a different speed, next 30 minutes at a different speed, and I'm required to find out the average speed, right? So can I do that first 30 minutes, 36, right? Next, 30 minutes, 72, 36 plus 72 by 2 directly, whatever comes the answer, right? So 6 plus 2 is 8, 7 plus 3 is 10, 108 by 2, that is nothing but 59 kilometer per hour, right? 59 kilometer per hour. Can I always, use this as the answer? Probably not. And let us see the reason behind this. Okay. Now, now your total average speed is nothing but the average distance covered by the total time covered. Okay. So we are saying that first 30 minutes it ran at a speed of 36 seconds. Okay. So 36 kilometer per hour. Okay. So at a speed of 36 kilometer per hour. If I can, so now let us convert everything into your meter per second. So if I convert into meter per second, I would do into 1000 by 3600. Okay. So what we can do, let us, do this math. So this will be 5 and 18. So remember, anything which is given in kilometer per hour, you want to convert it into meter per second. So if it is x kilometer per hour, just multiply 5 by 18 to that, and it will be this much meter per second. Okay, so in this scenario, it will be nothing but 36 into 5 by 18. So 18, this will be 2. So this is nothing but 10 meter per second. So it traveled 10 meter per second for first 30 minutes. Okay. Now let us see what happened in the next 30 minutes. So first 30 minutes, this is my this was the average, at this average speed, it moved for first 30 minutes. Okay. Now let us go to the next one. Next 30 minutes, it traveled at a distance of 72 kilometer per hour. And I showed you, just multiply this with 5 by 18 and you will get in meter per second. So 18, it becomes 4. So this is nothing but 20 meter per second. So what happened in this entire journey? For the first 30 minutes, the speed is given, that is 10 meter per second. Okay, okay, or 30 minutes also. Now let's convert into second. So first 180 second, sorry, your 1800 second, it traveled at this speed. Next 1800 second, next 1800 second, it traveled at a speed of 20 meter per second. Now if you see, the distance that it would have traveled in the first 30 minutes will be lesser, and the distance that it would have traveled in the next 30 minutes would be more. So do not jump in directly to add both the things, divide by 2 and get the average speed. No, find out step by step that what is the total distance covered by total time covered. Okay, so the next step would be, we need to find out total distance covered in first 30 minutes. Okay, it will be nothing but, what was the speed? Let's call it S1. So S1 will be 10 meter per second, 10 meter per second into, for how many seconds? 1800 second. So it will be nothing but 18,000 meter. Okay, so this is my first thing. Similarly, let us find out the distance covered in the next 30 minutes. So in the next 30 minutes, distance covered S2 in next 30 minute would be S2 equals to, what was the speed? Speed was 20 meter per second into same time 1800 second. So it will be nothing but 18 into 2, 36,000 meter. Okay, this is 2, right? Now I can find out what is the total distance traveled. We are trying average speed, not velocity. Okay, so to find out the average speed, so now I can say average speed would be total distance covered by total time elapsed or total time taken, right? So in this scenario, what is the total distance? S1 plus S2. What is the time? First 30 minutes and second 30 minutes. Now let us start putting the values. First S1 was 18,000. Next S1 was 36,000. And total time was 3600. So that is nothing but 1800 plus 1800, right? So if we solve it, it would be now very simple that this is 54,000 by 3600, two zeros cancel out. This is 18 two zer, this is 18 three zer. So we have 30 by 2, that is nothing but 15 meter per second. Okay, now you may argue that okay, one was 10 meter per second, another was 20 meter per second, right? If you would have just added 10 plus 20 and did by 2, you could have still got 15 meter per second. Yes, you would have got the right answer, right? Remember, students, when it is given in terms of time, so while calculating average speed, while calculating average speed, if your it is given in terms of a time that for t1 time, for t1 time speed was v1, for t2 time speed was v2, for t3 time speed was v3. Yes, you can still directly apply v1 plus v2 plus v3 by t1 plus t2 plus t3, and you can still get the average speed. So you may use it if you want to solve problem quickly in for any entrance exam, right? But I first wanted to a make you understand the concept behind it, and in the next problem that we are solving, you would see everything would change if I make a small tweak to this problem. Okay, so the tweak will be like this. Okay, okay. So the tweak will be, suppose I'm saying a motorist travels travels first half distance. It travels first half distance. Okay. Uh, So what was the total distance it has covered in the previous case? It was 36 plus 18,000. It was 54,000, right? So 54,000 meter. So let us divide it by 2. So we get 27,000 meter. So if I would have said the motorist traveled half of the distance at a speed of, your one was 10 meter per second, 10 meter per second, and the next half speed at 20 meter per second. Okay, it traveled the first half distance at a speed of 10 meter per second and next half distance at a speed of 20 meter per second. So I have taken time out of this equation. Okay, and then I'm asking what is the average speed. So in that scenario, if you see, things would change, because because this is how it would be. In that scenario, your average speed again would be total distance by total time. Okay, if for the first half distance the speed was 10 meter per second, so half distance means 27,000 sorry 27,000 meter. So the time taken taken to travel first half distance, how much it will be? It will be nothing but the distance traveled was distance by your speed, right? So distance was 27,000 by speed was 10 meter per second. This goes, one zero goes out away. So this is 2700, 2700 second. Okay. Similarly, what is the time that is elapsed in the second half? In the second half, for these 27,000 meter, it traveled at a speed of 20 meter per second, right? So 1010 will get cancelled out. Okay, so this would be, this is 2700. Then it would be your, how much? Your to be 1350 second, right? So 2700 second and 3500 second. Now we have got the two times, we have got the distances, and now let us calculate the average speed. So average speed is total distance by total time. So total distance s1 plus s2 by s1 minus by t1 plus t2. Let us just put in these steps only. Okay. So S1 total distance was 27,000 meter, plus S2 was also 27,000 meter, by your T1 was 2700, plus T2 came out as 1350. So now let us find out what is the value of that. Okay, so in the numerator we are getting 54,000, by, in the denominator we are getting 50, and then 3 plus 7 equals to 10, and then obviously 2 1 3 and 1 4, so 4050 second, right? So we divide this, and if you find it out, it will for sure not be equals to your 15 meter per second, right? So if we want to find out what is the exact value, so we can, divide by 5. So I think, if you find it out, it will definitely not be 15 meter per second. So that is the thing that I wanted to get registered into your brain, that if we take time out of the equation and supply that, okay, first half it traveled at this speed and second half it traveled at this speed, at that time your average speed would not be the simple average of both the speeds. Okay, so, and this is the reason. Okay, so that's why when you are calculating average speed, don't blindly just do an average. See whether your problem is in terms of your time or in terms of your distance. And then if you are writing a board exam, I would always advise you to go through total distance by total time, this approach, because when you do it step by step using this approach, obviously your concept on that would get cleared. Okay, good. So I think with these two practice problems, let's move on to the next part. Okay. So we had we had seen four physical quantities so far. Okay. So we saw distance, displacement, speed, and velocity. Okay. And we have also seen that the relationships between them, right? Okay. So I can say that your V is nothing but ds by dt, or your delta s by delta t, or rate of change of position is nothing but speed, right? So this thing already we know. So this is what we have already seen. Now let us go into acceleration. Okay, so let us go into the next thing, acceleration. And this is defined as, the rate of, and again let's go with first with average. So acceleration is defined as the rate of change of speed with time, right? So I'm saying that suppose I started my journey at a particular speed, uh, and then after some time I increased it to some other value. Then in that time of time interval, whatever was the change in my speed upon time, that would be my average acceleration. Similarly, there's a word called deceleration. There's a physical deceleration. Okay, so whenever you are decreasing the speed, right? So we say we apply a brake in a car or a bike to slow it down, right? So we are actually applying deceleration, or you can say negative acceleration, whatever you want to call that. Okay, so that is completely on. Okay, so yeah, so deceleration or negative acceleration. So I'll say that we denote it mostly with letter A. So average acceleration is change in speed upon time. Similarly, if I want to define instantaneous acceleration, obviously it would be limit delta t tends to zero. So at any given instant, right? So your difference in time would be almost zero. Change in speed by change in time, which we can also say dv by dt or d by dt of speed, that is your instantaneous acceleration. Okay, so here one thing which I intentionally changed. So remember students, for distance, you have the concept of distance and displacement. Similarly, for speed we have your speed and velocity. Sorry, speed and velocity. But whenever it comes to acceleration is always a vector quantity. So it comes from change in velocity upon time. Okay, so this is change in velocity upon time. If we want to know the magnitude, then we can say the magnitude is delta V by delta T. Okay? Okay? And everything else remains same. So if you want to express in terms of the vector symbol, you can go by vector. For calculating magnitude, you can just go by dv by dt. Okay, so this is instantaneous acceleration, this is average acceleration, and now let us quickly see the units and dimensions of this physical quantity acceleration. So unit would be nothing but velocity by time. So what is the unit of velocity? It is in SI, it is meter per second by second. So it is nothing but meter per second squared. So this would be the SI unit, and the CGS unit would be obviously centimeter per second squared. SI unit, CGS unit. Okay, so and then obviously we saw the dimensions also. Okay, so now let us do one quick small practice problem on this. Okay, okay, so one quick practice problem on this. So say a particular body is moving very randomly, and it is changing its velocity with reference to time very quickly. Okay, such that its position is given as s equals to suppose your uh, 3t square plus 5t plus 16 plus suppose TQ. It is given like this, right? Such that where S indicates your position and this variable T is time. So we are saying that this is position, this is time. So this graph is something in such a way. It's a the highest power is 3, so which is we know that if the highest power uh, is 3, then obviously it cannot be a straight line, right? So it's traveling a zigzag path. So somebody tells you find out find out the instantaneous velocity or magnitude of instantaneous velocity at t equals to 5 seconds, and also tells you to find out instantaneous acceleration. Okay, so let us see how we would solve this thing. So we know what is the formula for instantaneous speed. So this is nothing but v equals to ds d by dt of s, or ds by dt. Okay, so we need to just solve this derivative. So d by dt of 3t square plus 5t plus 16 plus t cube. Okay, which will be nothing but all these are added with plus sign, so I can separate them out. So I can say d by dt of 3t squared plus d by dt of 5t plus d by dt of 16 and d by dt of t cube, right? Now let's start solving. We know derivative of a constant is 0, okay? And in other cases, we have constants which will take outside of the derivative. So let's keep solving it. So obviously, it would be this 3 being a constant will go out of the derivative sign. So it will be 3 d by dt of t squared plus, again 5 is a constant, it will go out of the derivative, 5 d by dt of t plus, this is already gone as 0, so I'm not writing it. Here there is no constant, it's directly d by dt of t cube, d by dt of t cube, right? Now, using the formula, dy dx of x to the power n equals to n x to the power n minus 1. We'll use this formula obviously to find it out. So this is nothing but 3 into d by dt of 2t to the power 2 minus 1 plus 5. Here the coefficient is, here the power is 1. So this is nothing but 1 t to the power 1 minus 1 plus 3 t2 to the power 3 minus 1, which is nothing but 3 into, this is 2t, right? And this is 5 into, anything to the power 0 is 1, so it will be 5 into 1, that is 1, plus 3 into t squared. So that is nothing but 60 plus 5 plus 3t square, or if you want to rearrange it, put it like 3t square plus 60 plus 5. So now this is the equation that you found. So this stands for the instantaneous speed. Now if you see here, the interesting thing is, why do we call instantaneous speed? Because if you see, if I put different values of t at any given point of time, the velocity is changing, right? So that is why we are interested to find out the instantaneous. And in my problem, it has asked me to find out v instantaneous at t equals to 5. So I'll just put the value of t equals to 5 and get the answer. So 3 into 5 square plus 6 into 5 plus 5. So that is nothing but 3 into 25 is 75 plus 30 plus 5, that is nothing but 110 meter per second. Oh, or rather than saying meter per second, we should say distance by, or length by time, because we do not know in this problem, it has not given us what is the unit here, right? So it has not asked us to use the SI unit. So if it is not asked to use SI unit, do not by default use SI unit. Uh, yes, so that is what I just wanted to say. If there's an indication that use SI units, then that is absolutely right. It is 110 meter per second. If not, just keep it like length by time or distance by time. That's it. Similarly, now what will be the acceleration? What will be the acceleration? So we know acceleration is nothing but d by dt of v, right? So now I have got the equation for v. I'll put it here and find out the equation for acceleration. So let's go ahead. D by dt of 3t squared plus 6t plus 5. Again, all these three are separated by a plus sign, so I can separate them. I'll say d by dt of 3t squared plus d by dt of 6t plus d by dt of 5. Again, we know derivative of any constant, the 5 is a constant, so obviously this one would be 0. And here, again, 3 would go out of the derivative sign, 6 would go out of the derivative sign. Let's keep solving this. Okay, so that will be nothing but 3 d by dt of t squared plus d by dt 6 d by dt of t. That's it, right? Because this is only 0. So which is nothing but 3 into 2t, t to the power 2 minus 1, that is 1. So I'm directly writing 2t plus 6, 1 into t to the power 1 minus 1, that is nothing but 1. So I'll put 6. So that is nothing but 6t plus 6. Okay? So now, if it is 6t plus 6, now I have got the equation for my acceleration, and by putting a instantaneous at t equals to 5. So I'll put the value of t as 5. So in the fifth second, the acceleration was 6 into 5 plus 6, that is nothing but 36. 36, we'll say distance by time square. Okay, do not go ahead and directly write meter per second square. Okay, because if it is given in the problem to go with the SI units, you can go by meter per second square, or better put distance by time square or length by time square. That's it. Okay, yeah. So pretty simple problems. Okay, so now the next thing that we would do is we would we would understand these relationships using the graphs, right? So we saw when when position of something was not changing with time, right? So we got a straight line, okay? So and this indicates that something is at rest, okay? And we can find it out with graphically also, because in any graph, what does the slope indicate? Slope indicates nothing but the variable along the y-axis by variable along the x-axis. So in this case, slope is nothing but variable along the x-axis, that is s by here, this is time. So s by t, so that is nothing but your velocity, right? So this also indicates that, and in this case, what is the slope? So this theta is nothing but 0. So your your slope here is 0. And if your slope is 0, that obviously indicates it has got no speed. And if it has got no speed, this also proves that this is at rest. Okay? Now, Let us change it slightly and let us go to the next graph. Okay. So say something, yes. So we are saying that let's say that something is moving. Okay. So if it is moving, if this is the graph, right? So if I can say that the position S is given at uh, some mx plus t, right? So it has it if it's straight line. Okay. So in that scenario, if you see the slope here, if it is theta 1, then your slope at this point would be your tan theta 1, and here also it would be theta 1 or theta 2 if you say tan theta 2, but we know theta 1 equals to theta 2, or obviously your tan theta 1 will be equal to tan theta 2, and obviously slope throughout is constant, and we know that slope of your a straight line is always constant. So this also indicates that a straight line in the position time graph indicates not rest, but it indicates something called as uniform velocity. Okay, that something is moving at a uniform velocity, and when we are saying uniform velocity, the speed is not changing and the direction is also not changing. Always remember this thing, that we know that velocity is a vector quantity. So if speed is same but the direction is changing, just so for example, you tie a stone to one end of a string and start rotating that, right? And assume that you are rotating at a particular same speed. So though your speed is not constant, that the direction changes every second. So that's an accelerated motion. So we will not say that that is going at a uniform velocity, right? So in the speed time graph, this is how your uniform velocity would be shown. Now, suppose if something is accelerated, then what will happen? So we know that in the speed time graph, in the speed time graph, slope indicates slope indicates your velocity. So if it is accelerating, then obviously here, if my slope was this, here slope would be more, here slope would be more. If slope is like this, then this would be the shape of my graph. So the graph would be something like this. So remember students, an upward trending graph, right? This indicates acceleration. Again, we are not, from this graph we will not be directly able to say whether this is uniform acceleration or not. We are only saying that yes, it is accelerating. Similarly, if the slope is negative, then it would be deceleration. Okay. Now, this is about position time graph. Similarly, I would encourage you to draw velocity time graph yourself as a task and obviously play around it so that you would get more concepts related to that. Okay. So let us do one thing. Right now, I would be talking about the kinematics equations that we would use, and we would do two practice problems to understand some concepts related to that, and few of the theory I am consciously deferring to the next session, and that we would again come and touch over there. Okay, so so let us go into the three kinematics equations that we have studied in our high school life, right? So we had studied S equals to ut plus half at squared. We had studied V equals to u plus at, and we had studied that your v square equals to u square plus 2as. Okay, so these three kinematics equations, we would see different way of deducing them, use either using your graphical method or using your uh, differential calculus, your derivatives and integration. We would see them in the next session. Today, I'm more interested to show you or help you go through one or two practice problems so that the concept of frame of reference and these equations gets registered in your thought process. And obviously, in the next session, we would do some more practice problems on that so that things would be clearer to you. Okay, so let's move on to something interesting. Now, here in your high school studies, you had also seen that, okay, let me rewrite that. S equals to ut plus half at squared. So what are the considerations here? Consideration number one, this is a motion in one dimension or a straight line. Okay, so we are assuming that your displacement, acceleration, velocity, everything is in a straight line. Okay, and then the second assumption here is your a or the magnitude of your a, both magnitude and direction is constant. Okay, I repeat, your kinematics equations hold good only when we are talking about motion in one dimension and only when your acceleration, sorry, not magnitude, the entire acceleration, magnitude and direction are constant. So S equal to ut plus half at square we studied v equals to u plus at, and we studied v square equals to u square plus 2as, such that u is your initial velocity, where v is your final velocity, and a you know, t you know, s you already know, so I'm not writing them again. Okay, in high school we had also remembered a concept that this is for acceleration, but whenever there's a deceleration, right? So this formula we were changing as ut minus half at squared v equals to u minus at, and v square equals to u square minus 2as. Okay, so we had kind of remembered these formulae and we had solved problems in our high school level. So today, using the frame of reference, as I said, you try to understand frame of reference and you need not mug up few things, and this is one of those things. Okay, so we would see how we would use it in the next two practice problems. Okay, so say first practice problem. So a motorist a motorist is moving at a speed of, or at a velocity of, say your 72 kilometer per hour, suddenly sees a hole in front of him, and he finds a hole in front of him at 100-meter distance. Okay, how much how much deceleration, or at how much brake should he apply should he apply to save him from falling in that hole or pothole, whatever you want to say, into that pothole. Okay, now let us try to solve this problem. So we know that in our high school studies, we used to remember it that okay, somebody is moving and you are applying a brake. So obviously you are doing deceleration. You are doing deceleration, right? And there we had used a formula of using minus, and we have marked it up. Now let us see how we would use the frame of reference so that we need not remember that formula. Okay, so let us try to depict this problem graphically. Okay, we'll depict this problem graphically. So let me take a frame of reference. Okay, frame of reference, and I'm intentionally taking two dimension because we are talking about motion in one dimension. Even if I take one dimension, that is good enough. But I'm still just putting two dimensions. Okay, so suppose here was that motorist. Okay, so say it was a car. Okay, car is also a motor vehicle, right? So I can still say it was a motorist. So from here the person sees that at a distance of 100 meter there is a pothole. Okay, and he wants to save himself, and I said 72 hour. So he applies a brake. So he applies a brake so that he can stop before this, right? So in this scenario, if I take this as my frame of reference, and I said you will first define something as a positive direction, okay? So let us see that there are two guys. One is Bob, and say there's a lady Alice, right? So says Bob starts solving this problem, and Bob define this as his frame of reference. Okay, so in Bob's thing, right? So your displacement is along this direction, right? And if he applies the brake, your acceleration will be in this direction. Okay, so in case of Bob, what it will be? Let us try to solve it with this thing. And I said, after you have defined the frame of reference, in Bob's frame of reference, this is the positive x-axis. So this is positive x-axis. Okay. So anything along this direction, we will denote with a plus. Anything along this direction, we would denote with a minus. Okay. Because they are vectors, and any vector along this will be positive because Bob has taken this as the positive direction. Anything along this would be taken as negative. Okay, so let us go by our equation. Okay, so here we know S is given. So your S is given as 100 meter. Okay, his initial velocity, this was also along this direction, right? So initial velocity's magnitude is given as 72 kilometer per hour. Okay, I can multiply 5 by 18, so that is nothing but 20 meter per second. Okay, and he wants to, at least if he can stop here, if he stops here, then he will not fall in the pot, right? So can I say that final velocity magnitude, it should be 0. Okay, now all that I need to find out how much of brake he should apply. Now, I know that I can use, obviously, which formula of your, which basic kinematics formula? I can use S equals to ut plus half at squared. Now, we need not remember, we need not mug up in terms of the direction. And let us see how we will derive the directions using the your frame of reference. So we said in this frame of reference, this is the positive direction. If this is the positive direction, can I say that here your displacement is from here to here? So displacement is positive, correct? So S would not change. Initial velocity, this was also along this direction. So this would continue to be positive. Time is a scalar, so we need not attach any direction to it. Plus half, again a constant, we need not attach any direction to it. A, A here Here is the trick. If you see, A is in opposite direction. So will this be substituted? Will this be substituted by S is positive, U is positive, T is positive, half nothing to change. I'll say minus A into T squared, or that becomes ut minus half at squared. So we need not mud up the formula and see we have still arrived at the same place, right? And let us put the values and we can solve the problem. So if s equals to ut minus half at squared, so we can say your s is 100, initial velocity was 20 into, okay, okay, sorry, I will not use this formula, okay, because I do not know the time here. So rather I can use this formula, right? Your v square equal to u square plus 2as, right? Because I know v, I know u, I know s. Yes, I should use this formula. But again, v is along that direction. We would not change the sign. U, same direction. It is also positive. But here, if you see, A is negative. So that's why we would say V square equals to V square minus 2AS. Okay, so this gets substituted. Now put the values. What was the final velocity? It was 0. So 0 equals to U square. It was 20 square minus 2. We need to find out A, and distance is given as 100. So solve it. So this is 400 equals to 200 A, or A is nothing but 2 meter per second square. So if he applies a brake which can produce a deceleration, of 2 meter per second square, then obviously he or she would not fall in the pothole. Now, let us see the same problem in the next 2 minutes quickly from Ellis' perspective, because I want you guys to understand this concept rather than mugging it up. Okay? So if Ellis were to write this, how she would have done? Okay? So for Ellis, now for Ellis, suppose she chose this as the axis. Okay, if she chose this as the axis, then your origin is here. Okay, now everything would be reversed. So for Alice, now your this practical scenario is not changing, but for Alice, initial velocity is in the opposite. So for her, this is the positive direction. So initial velocity is in the negative direction. For her, acceleration is in positive direction, and for her the displacement, that is also in negative direction. Okay, so we can just, and final nothing, so we can just leave it like that. So that is 0 only. So 0 equals to u squared plus 2s. So for her it will be again u squared, so negative. So u was in this direction, so it was negative, and negative square is again your, yeah, so it will be for her minus u squared plus 2as, or again the same thing comes up. So 2as equals to u squared. So again 2 into your a into s was again 100, and u squared was 20 squared. So again a is 2. So this is the fun of it, that when you change your frame of reference, the positive and negative convention, everything gets reverted. So that can be solved accordingly. Similarly, we will use this concept in our next class to solve problems related to, say, I drop something from a height, right? Or if I'm throwing a stone upstairs. So we had again multi it up that if it is from top to bottom, always use positive. If it's bottom to up, your A will be minus, right? So that's how we have remembered in high school. But we will see using these same formulae or these same concepts how that would be resolved. So I think this is already too much of information in one shot, and obviously I have started going tired as well. So we'll take a logical pause here, and we would meet in the next class with the continuation of the topics. Thank you, students.